This video is about trig substitution. We're going to look at another technique to evaluate the integrals using trig substitution. There are some integrals where multiple methods, multiple techniques will work, but one technique might be easier than the other. So practice a lot of evaluating integrals. Okay, because we have learned quite a few different techniques of evaluating integrals already. So 8.4 trig substitution, remember the basic identities. Sine square x plus cos square x is 1. Tangent square x plus 1 is secant square x. Cotangent square x plus 1 is cosecant square x. Sine 2x is 2 sine x cos x. And we can also divide both sides with the 2 to isolate the sine x cos x. Cosine 2x takes three different forms. It can be written as cos square x minus sine square x. It can be written as 2 cos square x minus 1, and also written as 1 minus 2 sine square x. So if you want, you can isolate the sine square x and the cos square x in terms of double angles. Okay. Also remember the derivative formulas for inverse trig functions. I only remember the derivative of sine inverse x, tangent inverse x, and secant inverse x. And for all the functions with the co in the front, cos inverse x, cotangent inverse x, you really just have to put the negative in the front of your derivative. Okay. Which type of integrals we can handle with the trig substitution? There's a few examples. We can evaluate these integrals with using trig substitution. Square root of 1 minus x squared dx. Integral of 4x squared plus 9x squared dx. So all these are the types of integrals that we can evaluate using the trig substitution. Okay, there's basically three different kinds of problems you will be seeing using the trig substitution that we can evaluate. Let's look at the first type, trig integrals involving trig substitution. So anytime you see square root of a squared minus x squared, square root of a squared plus x squared, square root of x squared minus a squared, for some a greater than 0, you can often evaluate the integral by making a substitution involving a trig function, hence the name trig substitution. First, we are only going to focus on square root of a squared minus x squared. Again, if you look at the back integral formulas, x squared is in the back in the sine inverse formula. Okay, x squared, so you have something similar. Square root of 1 minus x squared is in the sine inverse formula. So if you ever see square root of a squared minus x squared, where a is greater than 0, we're going to let x be a sine theta. Okay, where theta lies between negative pi over 2 to positive pi over 2. We can eliminate the square root as follows. Okay, let's see. So square root of a squared minus a squared minus x squared, if we replace the x by a sine theta and square it, we are able to pull the a out of the square root, and we have a much simpler integral to handle. All right, so let's check. Square root of a squared minus x squared. So this one looks like I do have x squared in the back, so I'm gonna use the substitution here. What's my a? If you try to compare 4 with a squared, that tells me a is equal to 2. So I'm going to let x equal to 2 sine theta. Okay, x be the 2 sine theta. And this will give me dx be 2 cos theta d theta. Okay, let's go ahead and replace the x's and dx by, so on the numerator, in the numerator, I have 1 times 2 cos theta d theta. And the x is getting replaced by 2 sine theta squared. And then I have square root of 4 minus 2 sine theta squared. This turns out to be 2 cosine theta d theta divided by 4 sine squared theta, and then square root of 4 minus 4 sine squared theta. Okay, so inside the square root, I have a 4 here, which I can pull out 2 cos theta d theta divided by, I'm going to pull the 1/4 out here, sine square theta, and inside the square root, I have a square root of 4, which square root of 4, I can pull out the 2 from the square root. So I can pull the 2 out from the square root, and I would have 1 minus sine square theta. Okay, so I also see the 2 in the numerator and denominator will cancel. I'm left with cos theta d theta divided by sine squared theta. What's 1 minus sine squared theta is cos squared theta. So we have square root of cos squared theta. Okay. A little bit more simplification. We have cos theta d theta divided by sine squared theta. And square root of cos squared theta, square root and square will cancel each other, so I'm only left with cosine theta. I have a cosine theta sitting on the top and a cosine theta sitting on the bottom, so that is gone, and I'm left with 1 over sine squared theta d theta. And 1 over sine squared theta is cosecant square theta d theta. Integral of cosecant squared theta it's one of the elementary integrals that you should remember, one of the integrals from the table formulas in the beginning. So integral of 1 over 4 cosecant squared theta d theta is 1/4, still stays there. Integral of cosecant squared theta is cotangent theta plus a c. Now if you recall, derivative of cotangent theta is negative cosecant squared theta. Okay, so this is our integral, but we're not done because we want to go back to x. We did not start with x in our problem. We did not start with theta in the problem. We started with x, so we want to go back to x. So let's look at the relationship that we used in the beginning. We said x was 2 sine theta. From here, we can say x over 2 is sine theta. If you recall, the sine theta is SOHCAHTOA. Sine theta is opposite over hypotenuse. SOHCAHTOA. So opposite is going to be x, hypotenuse will be 2. And if I try to find the other leg using Pythagorean theorem, this would be 4 minus x squared. Just using Pythagorean theorem to find the other leg. Now, I'm ready to write my integral in terms of x. So negative 1/4. Tangent is opposite over adjacent, and cotangent will be adjacent over opposite. So cotangent theta would be adjacent over opposite. So I'm going to have square root of 4 minus x squared over x plus a c. That's it. We evaluated that integral using trig substitution. So again, if you have square root of a squared minus x squared, means x squared is behind, or the second term or the last term, whatever you want to call it, you do want to try x equals a sine theta. Okay, let's check out the next example. If our integral contains a squared plus x squared, so if you ever see a squared plus x squared in the square root or without square root, where a is greater than 0, our substitution will be x equals a tangent theta. The reason why is if you look at the derivative formulas, so only the tangent derivative formula, when you do the derivative of tangent inverse x, you have 1 over 1 plus x squared. So let's go back and look at this example. This is a definite integral, so we will worry about the bounds a little later. For now, I'm just going to focus on the evaluating the integral. Okay, so what is my a in this case? Looks like a is 3, because it's 3 squared. 3 squared is 9. So this integral can be written as 0 to 3, 1 over square root of 3 squared plus x squared dx. So I'm going to let x be 3 tangent theta, dx be 3 secant square theta d theta. Okay, so 0 to 3. These are still the x bounds. We can go ahead and change the bounds, or I will actually drop the bounds for now, and I'll come back and put the bounds at the very end. Okay. So for now, I'm just going to focus on evaluating the integral 1 over square root of 3 squared plus x squared dx. We will take care of bounds at the very last. Okay, so let us see now. Let's go ahead and do the substitution. We have 1 over square root of 3 squared plus 3 squared tangent squared theta. And on the top, we have 3 secant squared theta d theta. All right, it looks like I do have 3 squared inside the square root, or 9 inside the square root. I can pull out square root of 9, and I can pull out the 3 from the denominator. I also have the 3 in front of secant squared theta that I can pull out from the top, and the bottom turns out to be 1 plus tangent squared theta. So I pulled out a 3 from the square root of 9, or I pulled out a 3 from the square root. Okay. Now what is 1 plus tan squared theta equal to? 1 plus tan squared theta is secant squared theta d theta on the top. 1 plus tangent squared theta is secant squared theta. Now, are we able to go ahead and do the square root? Square root and square will cancel in the denominator, so I'm just left with secant theta. Okay, so secant squared theta on the top, secant theta in the denominator. One of those will be gone, and I'm just left with secant theta d theta. Secant theta d theta. And secant theta is one of the special integrals that we saw in the previous sections. How do you evaluate the secant theta integral? You have to multiply top and bottom with, really quick, I'll show you. You have to multiply secant theta. You have to multiply top and bottom with secant theta plus tangent theta over secant theta plus tangent theta d theta. Now we can let secant theta plus tangent theta be the u, and we have the derivative sitting on the top when I do distribute the secant theta here. So I'm going to have the derivative du over u, which turns out to be natural log of u plus c. And that's how the integral of secant theta is natural log of secant theta, natural log of secant theta plus tangent theta plus c. Okay, so we're not going to stop over here because our problem did not have any thetas. Our problem did have x's, so we want to go back to x's. Always draw your right triangle, okay? To go back to x's, always draw your right triangle. So my right triangle would be, I did let, in the beginning, we did have x equals 3 tangent theta. We did let x equals 3 tangent theta, so we can say x over 3 is tangent theta, and tangent is opposite over adjacent. So when you draw your triangle, this is where the theta is. Opposite would be x, adjacent would be 3, and if I find the hypotenuse using Pythagorean theorem, it would be x squared plus 9, or 9 plus x squared, doesn't matter how you want to write it. I'm going to write 9 plus x squared. Okay. Now I have my relationship, and I'm going to plug these in terms of x's. What is secant theta going to equal? So my integral turns out to be natural log of secant theta. Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse, so we would have hypotenuse, not 9 squared, it would be just square root of 9 plus x squared. Hypotenuse divided by adjacent, that would be secant theta, and tangent theta would be opposite over adjacent. What is the opposite here? The opposite is x, adjacent is 3, plus a c. Do not forget, we need to bring our bounds. We had the bounds going from 0 to 3, so go ahead and plug the bounds. Natural log of square root of 9 plus x squared over 3 plus x over 3. We did not need the c in this case because we have the bound from 0 to 3. So plug the bound from 0 to 3 now. Let's plug the upper bound, then the lower bound. So 0 to 3. So if I start by plugging a 3 in here, I will have natural log of square root of 9 plus 9 is 18 over 3 plus 1 minus natural log of square root of 9 over 3, that would be 1, plus 0 over 3 is just 0. And natural log of 1 is 0, so that does not even matter if you write it or not. So no need to write natural log. We know that it's equal to 0. So that's my integral. That's what my definite integral comes out to be. Okay. Next example. If you ever see the kind of substitution or the integral inside your integral, you ever see x squared minus a squared, that means you have x squared in the front, not in the back like it was in the case of sine theta. So x squared is in the front. In that case, we want to let x be the a secant theta. Okay, we want to let x be the a secant theta. If I let x be the a secant theta, we would be able to use our trig identities, Pythagorean identities, and have just a tangent theta out without any secant theta hanging out there. Okay, so let's go ahead and look at an example of this kind now, where we have x squared in the front, x squared in the beginning. So I'm going to let x be 5 secant theta. Dx would be, what's the derivative of secant theta? It is secant theta tangent theta d theta. So I'm ready to substitute now. So I have 5 square secant squared theta d theta minus 25. So when I plug x as 5 and I square it, I would have 25 secant squared theta minus 25. In the denominator, I would have 5 secant theta, and the dx turns into 5 secant theta tangent theta d theta. A little bit simplification, I have a square root of 25. I can pull out a 5 from here. So 5 can be pulled out from the numerator and denominator, and there's another 5 in the numerator that we can pull out. So I'm left with secant squared theta minus 1 times secant theta tangent theta d theta divided by, let me write in the next line. Looks like I write big and there's not enough space. Okay, so this can be written as, I can pull out a 5 from the top, another 5 from the top numerator, and my numerator now is secant squared theta minus 1 secant theta tangent theta d theta, and the denominator, I do have secant theta. Okay, so what is the square root of secant squared theta minus 1? We know secant squared theta minus 1 is tangent squared theta, and when I do the square root, it just turns out to be tangent theta. So this 5 and 5 is gone. We do have secant theta, tangent theta, another tangent theta, d theta on the top, and then secant theta in the denominator. Now, one of the secant theta on the top and bottom, there is one on the top, one on the bottom, that will be gone. So this integral turns out to be 5 tan squared theta d theta. How do I evaluate this integral? We can break tangent squared theta into secant squared theta minus 1 again. That's how we can evaluate, because there's no use substitution or any other techniques that would work here. So we can use the trig identity back, and now I can isolate the two integrals. So I can do secant squared theta d theta minus 1 d theta. Okay, what's the integral of secant squared theta? Is there a function whose derivative is secant square theta? Yes, it is tangent theta. And then integral of 1d theta is just a theta. And then plus a c. This is what our integral, actually the 5 would go to theta as well. So there would be a 5 next to theta also. Now, it's not all done. We do have to go back to x's because we did not start with the theta. So we need to go back in terms of x. How do we go back in terms of x? So let's look at our substitution we did in the beginning. We had called x as 5 secant theta. So we're going to use this relationship. So we did let x equals 5 secant theta. From here we can say secant theta is x over 5. Okay, go ahead and draw your triangle now. Right triangle. Cosine is adjacent over hypotenuse. And secant would be hypotenuse over adjacent. So hypotenuse is x, adjacent is 5. Hypotenuse over adjacent would be secant theta. And now the other leg would be x squared minus 25. If you simplify the other leg, it turns out to be x squared minus 25. X squared minus 25 is the other leg. Okay, yep. Adjacent over hypotenuse, hypotenuse over adjacent. Hypotenuse is x, adjacent is 5, and the other leg would be x squared minus 25 using Pythagorean theorem. Now let's go ahead and plug these back in terms of x. This integral, we have 5. What is tangent theta going to equal? Tangent theta is opposite over adjacent. So opposite is x squared minus 25 square root over 5 minus 5. What is theta going to equal? Notice theta would be equal secant inverse of x over 5. So from here we can say theta is secant inverse x over 5. 5 secant inverse x over 5 plus a c. And that's our integral. We can get rid of these 5's, but remaining is our integral evaluated. And we got it back in terms of x. Always remember, get it in terms of x because your problem did not have any thetas in the beginning to start with. So you must go back to x's. That's what we had in our problem. Next one, square root of 9 plus x squared looks like a simpler problem to me. I can clearly see we have 9 plus x squared. That tells me I'm going to have to use a trig substitution. X equals 3 tangent theta. And dx would be 3 secant squared theta d theta. Okay, let's go ahead and replace in our integral 9 plus 9 tangent squared theta, because you're substituting x here, but then you also have to square that x, because x squared would be 9 tangent squared theta. Okay. And dx is 3 secant squared theta d theta. All right, so let's see what can we do now. I see a common 9 inside the square root, so I can pull out square root of 9, which will leave me with the 3. I can pull out another 3, and I have 1 plus tangent squared theta secant squared theta d theta. What is square root of 1 plus tan squared theta? We have looked at it in the past. 1 plus tan squared theta is secant squared theta, and when I do the square root, it would be just secant squared theta d theta. Okay, our famous integral of secant cube theta looks like it's coming up over here, secant cube theta, which is, so this turns out to be 9 secant cube theta d theta. And the integral for secant cube theta d theta is, we have looked at it in the past. You can also use the reduction formula. 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta plus a c. Okay, so 1/2 secant theta tan theta plus 1/2 natural log of secant theta plus tangent theta plus c. Well, this is not all done because we must go back to x's. We cannot leave convert back to x. Convert back to x. That is nothing. Convert back to x. Okay, so we did let x was 3 tangent theta. So we can say x over 3 is tangent theta. Go ahead and draw your triangle. Tangent is opposite over adjacent. Opposite is x, adjacent is 3. My hypotenuse will be 9 plus x squared. Okay, so opposite over adjacent, and we found the hypotenuse. Now let's go ahead and plug them into our integral that we evaluated. In here, everything goes in terms of x, not in terms of theta. So I'm not going to simplify 1/9. I'm going to leave it like that for now. Or 9 in the beginning, 9 in the front. So I can say 9, 1/2. What is secant theta going to equal here? Secant is adjacent over hypotenuse. Remember, reciprocal of cosine? Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So secant theta comes out to be square root of 9 plus x squared over 3. And tangent theta is opposite over adjacent, which is x over 3. Plus 1/2 natural log of secant theta is square root of 9 plus x squared over 3 plus tangent theta is x over 3 plus a c. And that's what our integral comes out to be. Go ahead and simplify, distribute the 9 inside, and I believe 9 is going to cancel in the first portion of our integral. Okay, so I'm going to leave it at this point. Leave the last step for simplification for you to try. Let's see the next problem. Again, it's very important to identify what do you have in the front. Do you have a square in the front, or do you have x square in the front? If you have x square in the front, then you do want to call the x as a secant theta. Okay, in this case, a looks like it's 4. So I'm going to let x is equal to 2 secant theta. Dx will be 2 secant theta tangent theta d theta. Let's go ahead and do the substitution here. So we have integral 2 secant theta tangent theta d theta, and we are replacing x by 2 secant theta. So x squared would be 4 secant squared theta minus 4 to the power 3/2. Okay, so let us see. Might be a little bit easier to write it in terms of square root and the power 3. Okay, so from the denominator, I can pull out the 4 to the power 3/2. From the denominator, 4 to the power 3/2. What is 4 to the power 3/2 equal? So it's 4 to the third power square root, or square root of 4 to the third power. That's what this is, which is 2 to the third power, which is 8. So from the denominator, from the numerator, I can pull out a 2. From the denominator, I can pull out a 8. And this integral, I have secant theta tangent theta d theta divided by secant squared theta minus 1 to the power 3/2. Okay, now 2/8 can be written as 1/4 secant theta tangent theta d theta divided by secant squared theta minus 1 is tan squared theta. So this is tan squared theta to the power 3/2. And notice tangent squared theta to the power 3/2. This is going to cancel because it's the same thing as tangent squared theta square root to the third power. So square root and square can cancel, and we would be left with tangent to the third power in the denominator. I do have a tangent theta on the top, a tangent cube theta in the denominator. So I'm going to cancel one of those tangent theta, and I'll be having left with, so 1/4 secant theta over tangent squared theta d theta. So how do we evaluate this integral of secant theta over tangent squared theta? Let us see. I'm going to try to convert everything to sine and cosine because that's what I think might help. Cos theta. Tangent squared theta is sine squared theta over cos squared theta d theta. Okay, so looks like one of the cosines can be cancelled. I have two cosines on the top. So I'm left with, in my integral is 1/4 cosine theta over sine squared theta d theta. Okay, so cosine theta over sine squared theta d theta. I can do the u substitution here. So let sine theta be u, cos theta d theta will be du. So we have 1/4 integral of du over u, which turns out to be 1/4 natural log of u, plus c. I will take care of plus c at the end, which turns out to be 1/4 natural log of u was, no, I'm so sorry, this was sine squared theta. My bad. So this is not u in the denominator. We have u to the second power in the denominator. So that will change our integrand to u to the power -2 du, which is 1/4. U to the power -2 plus 1 is -1. And we also divide with -1, which makes it a negative here, plus a c. So that I can write it as -1/4. What did we call u in the beginning? U was sine theta plus c. Okay, just a little bit more. I'm going to write it as -1/4 cosecant theta plus c, although you don't have to, but we need to convert back to x. Convert back to x, okay? Convert back to x. We need to convert this back to x now. Let's go ahead and see, what did we call x in the beginning? X was, okay, for some reason my highlighter, now it is working. Okay, so we called x as 2 secant theta. Okay, so x was 2 secant theta. We can say x over 2 is secant theta. Draw your triangle. Reciprocal of cosine is the secant. Cosine is adjacent over hypotenuse. Secant will be hypotenuse over adjacent. And the other side, remaining side, would be x squared minus 4. Okay. Now what do? We just go ahead and replace. Cosecant theta is reciprocal of sine theta. Sine theta is opposite over hypotenuse. Cosecant would be hypotenuse over the opposite, which turns out to be this, and that would be the end of our problem. We evaluate that integral in terms of x. Okay, let's check out our next example. On this page, both number 6 and 7 are very similar. Actually, a little different. I also have an x in the numerator for number 7. Okay, so let's go ahead and try number 6. There's no square root in this case. That's okay. But I do know I'm going to let x be 6 tangent theta. Why tangent theta? Because I have a plus x squared plus a squared type of expression in the denominator. And dx would be 6 secant squared theta d theta. Okay, so that turns out to be 6 secant squared theta d theta over 36 tangent squared theta plus 36. Let's pull out the 6 from the numerator, 36 from the denominator, and I have secant squared theta d theta over tan squared theta plus 1. Okay, so if I simplify, I'm left with 1 over 6 secant squared theta d theta in the numerator, and tan squared theta plus 1 is also secant squared theta. So we can just get rid of secant squared theta and secant squared theta. We're left with 1 d theta, and integral of 1 d theta is just theta plus c. We have to go back to the x's, again convert to x. X over 6 is tangent theta because in the beginning we did call x as 6 tangent theta. And if I draw my triangle, actually we don't even need to draw the triangle in this case because I can clearly see from here. I can say theta is tangent inverse x over 6. So I'm going to plug it in there. 1/6 tangent inverse x over 6 plus a c, and that's it. That's what our integral simplifies to. Okay, let's look at example number 7. This one, right away looking at it, this problem looks like a very good candidate for u substitution. Go ahead and try it. It would work out. If you call 16 plus x squared as u, you have the derivative sitting on the top, or you can make the top the derivative of the bottom. So I'm not going to focus on u substitution in this video, but give it a try. It might be a little bit faster than the trig substitution in this case. So I'm going to focus on the trig substitution like we've been talking about. So I'm going to let x be 4 tangent theta. Dx will be 4 secant squared theta d theta. Okay, so on the top I have 4 tangent theta because of the x, and dx is 4 secant squared theta d theta. And in the denominator I have 16 plus 16 tangent squared theta. Okay, let us see what can I pull out from the numerator. Looks like I can pull out a 4, I can pull out another 4, and from denominator I can pull out a 16. There's no square root, so 16 would come out. The top, I can do 4 times 4, 16, and numerator and denominator, they both, I can pull out a 16 from there. The numerator is tangent theta secant squared theta d theta, and the denominator is 1 plus tangent squared theta. Again, know your identities really, really well. 1 plus tan squared theta, so 16 and 16 is gone. 1 plus tangent squared theta is secant squared theta. So this turns out to be tangent theta secant squared theta d theta over secant squared theta. Okay, which is tangent theta d theta. How do we evaluate the integral of tangent theta? If you recall, we have changed into sine theta over cosine theta d theta, and then we let cos theta be u, negative sine theta d theta will be du, or we can say sine theta d theta will be negative du. So this entire integral converts into negative du over u, which is negative natural log of u plus c. It's negative natural log of u was cos theta plus a c. Now we cannot leave in terms of x, we have to convert back to, or we cannot leave in terms of theta, we have to convert back to the x. Because we called x as 4 tangent theta, so convert back to x. We did say x is 4 tangent theta, so we can say x over 4 is tangent theta. Okay, if I draw my triangle, this is the theta, tangent is opposite over adjacent, and hypotenuse is going to be x squared plus 16. Okay, so my integral turns out to be negative natural log of cos theta. And what is cosine theta equal to? Cosine is adjacent over hypotenuse, which is x squared plus 16 plus c. Okay, that's what our integral comes out to be, and we did convert it back into the x form. All right, next example. This one we would have to complete the square in the denominator since we don't have any x's on the top, and it looks like x squared plus 4x plus 5 multiply to 5 add up to 4. It is not factorable either, so I'm going to go ahead and complete the square. quickly showing you how to complete the square. X squared plus 4x plus 5. And we want to complete the square. What number would complete the square over here? So I'm leaving it blank, pushing the 5 away. It's half of your b squared. So half of 4 squared, which is 2 squared, and you also have to subtract 2 squared. So my complete square would turn out to be x plus 2 squared plus 5 minus 4, which is x plus 2 squared plus 1. So when I complete the square, I have x plus 2 squared plus 1 dx. I haven't done any trig substitution. All I did is I just completed my square. Now, in the previous problems, we have seen, I'm going to make up space for myself. In the previous problems, we have seen that if you had 1 over x squared plus 1 dx, then we did use this is for the tangent inverse x. Integral of this is the tangent inverse x. So you've seen that. So this one looks a little similar to me, but instead of x, it's x plus 2. So that's okay. I'm going to go ahead and do the substitution. I'm still going to use a tangent inverse x here. So I'm going to let x plus 2 be tangent theta. And dx will be secant squared theta d theta. So let's go ahead and replace secant squared theta d theta over tangent squared theta plus 1. Now we can tackle this integral. This one is a lot simpler, a lot nicer than what I had in the beginning. What is tangent squared theta plus 1 equal to? That is also equal to secant squared theta. Now I have secant squared theta both in numerator and denominator, so they cancel each other, and I'm just left with theta plus c when I do the integrand. Now what is theta equal to? Go back to your relationship that we had in the beginning. So we did let x plus 2 was tangent theta. We can say theta is tangent inverse x plus 2. We're going to use this relationship, and our integral will evaluate to tangent inverse x plus 2 plus c when I plug the theta back in there. Okay. Let's check out the next example. dx over x squared minus 16x plus 11. It's actually not 16x. This is a typo. Change it to 6x. Okay, so this is a 6x. Okay. This is not a 16x. So x squared minus 6x plus 11 squared. What should I do here first? Again, it looks like I'm going to have to complete the square. So I'm going to do the work for completing the square on a side. X squared minus 6x. I'm going to leave some space and push the 11 away. What number should I add over here to complete my square? Looks like half of 6 squared. Half of 6 is 3, so I'm going to add a 3 squared and subtract a 3 squared. It turns out to be the completed square will be x minus 3 squared plus 11 minus 9, which is x minus 3 squared plus 2. Okay, so what else we can do here is now let's go ahead and call it dx over x minus 3 squared plus 2, everything squared. Again, I see a tangent in here with a as square root of 2. So I see, because if you have 1 over x squared plus a squared dx, that is tangent inverse x over a, right? So I see a tangent inverse here because of the plus in the middle, but a few other substitutions. Let's go back. I'm going to erase the work for completing the square to have more space for myself. So what I'm going to do is I'm going to use a clever substitution here. I'm going to let root 2 x minus 3 be the tangent theta. or x minus 3. Okay, we can do it in multiple different ways. Let's first go ahead and pull out the 2 really quick. So if I want, I can express it. I can pull out the 2 squared from, that's just an algebraic simplification. This would become x minus 3 over square root of 2 squared plus 2, everything squared. So I pulled out a 2 squared from the denominator. I pulled out a 4 from the denominator. Okay. You can multiply the 4 back in here and you would get the same thing back. So if you take the 2, you have 2 square outside, you can take the 2 back in and you would get, this would actually be a 1 here, since I pulled out a 2 from the parentheses. Okay. Now, this does look like a tangent to me, so I'm going to let x minus 3 over root 2 be the tangent theta. And that means 1 over root 2 dx be secant squared theta d theta. Okay, 1 over root 2 dx be secant squared theta d theta. Or we can say dx will be root 2 secant squared theta d theta. Okay, so let's go ahead and plug it in terms of u here. Again, you might have to carefully look at this little algebraic trick where I pulled the 2 out. You didn't have to. You could just leave the square root of 2 in front of, tangent theta. You could call x minus 3 as root 2 tangent theta. That was okay as well. All right, so now we have dx is equal to, I'm going to pull the root 2 out. We already have a 4 out. And the numerator becomes secant squared theta d theta. Secant squared theta d theta. And the denominator turns out to be tangent squared theta plus 1 to the second power. Okay, which turns out to be root 2 divided by 4 secant squared theta d theta on the top. What's tan squared theta plus 1 equal to? Tangent squared theta plus 1 is secant squared theta. But then I also have the square of it. Now, looks like one of these will cancel. And I would be left with root 2 divided by 4, 1 over secant squared theta d theta, which is one of the integrals from the table, I think. 1 over secant squared theta is, no, 1 over secant squared theta will be cos squared theta. It's not from the table, but we have to use the identity here. We know cos squared theta can be written as 1 plus cosine 2 theta divided by 2 d theta. And now we would just do the integral of the pieces. Integral of 1/2 d theta plus integral of 1/2 cosine 2 theta d theta. And that turns out to be root 2 over 4 is still out in the front. What's integral of 1/2 d theta? It's just theta divided by 2. And for cosine 2 theta, it would be 1/4 sine 2 theta. Cosine 2 theta would be 1/4 sine 2 theta. 1/4 sine 2 theta, right. And now a little more simplification, and then we will have to go back to x's. Root 2 over 4. Again, there's a plus c here. So that turns out to be theta over 2 plus 2 sine theta cos theta divided by 4 plus a c. Turns out to be root 2 over 4 theta over 2 plus sine theta cos theta divided by 2 plus a c. Now we are going to convert back to x. So let's see, what did we call tangent x in the beginning? Tangent or tangent theta. Tangent theta was x minus 3 over root 2. So tan theta was, we did call, I'm going to do it on a side here. Tangent theta was x minus 3 over root 2, right? Yeah. So draw your right triangle now. Theta is here. Tangent theta is opposite over adjacent. Opposite is x minus 3. Adjacent is square root of 2. Now I need to figure out what the hypotenuse will be, because I will need hypotenuse here also. So go ahead and use Pythagorean theorem and find out what your hypotenuse is. It's going to turn out to be x squared minus 6x plus 11. Minus 6x plus 11. Use Pythagorean theorem and evaluate, find out your other side. All right. So now, what are we left with? We are going to go back to the x's. So our final integral, I'm going to go back to x's, and I'm not going to bother about distributing the square root 2 over 4, but you can if you want to. What is theta going to equal? Theta will be tangent inverse x minus 3 over root 2. And sine theta would be opposite over hypotenuse. And cosine theta would be adjacent over hypotenuse plus a c. Now you can see in the denominator when they multiply, the square root will cancel. So do that in the next step. Get rid of the, do a little more cleaning up. Let's see if I have space. Root 2 over 4. Tangent inverse x minus 3 over root 2 plus root 2 over 8. There's another root 2 here, so that would just give me a 2 on the top. Yep, that would just be a 2 over 8, which is 1/4. 1/4 x minus 3 over x squared minus 6x plus 11. No square root, plus a c. And that's it. That's the end of this problem. Let's look at next. Stop for a minute and think about what trig substitution. Oh, for the previous problem, I think the one we just did, I believe, oh no, u substitution is not going to work. Okay, that's fine. Number 10, think about it for a minute. What trig substitution are you going to use? What trig substitution would work here? Which trig substitution can we do the u substitution? Give it a try. Pause for a minute and see if you can set up the integral and evaluate it by yourself. I think because I have x squared in the beginning, I'm going to have to go with the secant, and my a is 1, so that's even better. I don't have to worry about any a over here. So I'm going to let x be the secant theta, and dx will be the secant theta, tangent theta, d theta. So go back to my integral. I have secant squared theta, tangent theta, d theta, over x squared minus 1, which is secant squared theta minus 1 to the power 3/2. Okay, see if there's anything I can definitely use. I have secant to the third theta on the top now because there's 3 secant thetas, secant cube theta, and then I also have tangent theta d theta divided by secant squared theta minus 1 is tangent squared theta, but raised to the power 3/2. Now, if you understand the exponents, the rules of exponents, the 2 and 2 will cancel. So I would be left with secant cube theta, tangent theta, over tangent cube theta, d theta. Now, one of the tangent thetas can be cancelled, so my new integral is secant cube theta, d theta, over tangent square theta. Again, I think I'm going to go ahead and try to change them to Sine and cosine with the help. Let's give it a try. Let's change them to sine and cosine and see if it helps. So I have secant theta. I can write it as 1 over cos cube theta because it's secant cube theta. And tangent squared theta in the denominator would actually become sine squared theta over cos squared theta. And I still have d theta there. Now, let us see. Okay. So it looks like one of the cosines can be cancelled. I still have 1 over cos theta times sine squared theta. 1 over cosine theta times 1 over sine squared theta. Okay, what does that turn out to be? It doesn't really help me out, so it's not. Let's go ahead and write sine squared theta as cosecant squared theta and 1 over cos theta as secant theta d theta. Okay. What I can do here is now I can replace cosecant theta as 1 over cotangent squared theta, secant theta d theta. I'm going to distribute this in here. This turns out to be secant theta d theta plus cotangent squared theta secant theta d theta. Okay, so here cotangent squared theta times, let's see, 1 plus cot square, that's cotangent square times secant theta. Okay, let me write it a bit neatly here. Cotangent squared theta, secant theta, d theta. All right, so let's just call them number 1 and number 2. I'm going to evaluate them separately. Secant theta integral, I do know we have done that in the past. This one is equal to natural log of secant theta plus tangent theta. I already know this one. How about the cotangent squared theta, secant theta d theta? This one, cotangent is cosine over sine, so it's cos squared theta over sine squared theta, 1 over cos theta d theta. Looks like one of the cosines can be cancelled, so it's cos theta over sine squared theta. We can do the u substitution here, so I can let u be the sine theta and cos du will be cos theta d theta. Yep. So we can write that integral as du over u to the second power, which will turn out to be negative u to the negative 1 power, which is negative u was sine theta to the negative first power, which is negative 1 over sine theta. Okay, so let's go ahead and plug 1 and 2 back in here, and we have our integral now. So that turns out to be natural log of secant theta plus tangent theta minus 1 over sine theta plus a c. Okay, 1 over sine theta can be also written as cosecant theta. All right, now we have to go back to x's because our problem did not start with any thetas. Our problem had x's in there, so I'm going to get some space for myself to do the work for x's, to get back to x. Okay. Let's see, what did we call x in the beginning? What was our beginning trig substitution? I believe x was secant theta. Okay, so secant theta was x. We can put a 1 in the denominator if we want. And now go ahead and write your theta over here. Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse, so this will be hypotenuse over adjacent. Hypotenuse is x, adjacent is 1. Our third side would be x squared minus 1 using Pythagorean theorem. So we are ready to plug our values in. Secant theta was equal to x. Tangent theta here would be opposite over adjacent, which is x squared minus 1, opposite over adjacent. And sine theta is opposite over hypotenuse. Reciprocal of sine theta would be x squared minus 1 plus c. And that's what we are ending up with. Again, to summarize, remember your trig identities. And also remember your substitutions. Which trig substitution you're going to be using. If you have x squared in the x squared is your second term, a squared is first, then use a sine theta. If x squared is first term or second term with the plus in the middle, use a tangent theta. If x squared is first term and you have subtraction, use secant theta. So for the minus inside, you would think about sine theta or secant theta depending on if x squared is in the front or in the back. Okay. Next, I have two try me problems. So pause for a minute, go ahead and give these a try. Come back and check with me. I'm going to be working these out as well. Okay, we can pull out a square root of 9 from the parentheses. There is a 9 coming out. There's square root of 9 coming out as well. So we have cos theta over sine squared theta, 1 minus sine squared theta. Okay, that turns out to be 1 over 9 cos theta over sine squared theta. 1 minus sine squared theta is cos squared theta. When we do the square root, it would be just cosine theta d theta. Okay, looks like this is gone. 1 over 9 integral of cosecant squared theta d theta, which is 1 over 9 negative cot theta. So I need some space for the negative sign, which is equal to negative 1 over 9 cotangent theta plus c. Now we want to go back to x's. So x over 3 is the sine theta. So I'm going to draw my triangle. This is my theta. Sine theta is opposite over hypotenuse. This side would be 9 minus x squared. Okay, opposite over hypotenuse, right? So what is cotangent theta from this right triangle? Cotangent would be reciprocal of tangent. Tangent is adjacent, opposite over adjacent. So cotangent will be adjacent over opposite. Adjacent is 9 minus x squared. Opposite is x plus a c. That's what our integral turns out to be. Second problem. Because I have the x here, x squared plus 1 kind, I'm going to use let 2x be tangent theta, because this can be written as let 2x be tangent theta. Okay, and that would mean this would mean 2dx is secant squared theta d theta. Our dx is half of secant squared theta. Okay, so 1/2 secant squared theta d theta divided by 2x is tangent squared theta plus 1. Okay, 1/2 secant squared theta d theta over tan squared theta plus 1 is secant squared theta. When we do the square root, we are just left with 1 secant theta. One of the secant theta can cancel between numerator and denominator. So it's 1/2 secant theta. Integral of secant theta is natural log of secant theta plus tangent theta plus a c. No. Yes, that's right. Natural log of secant theta plus tangent theta plus a c. So now it's time to go back to x's. So I need to go back and see what did we call x in the beginning. We did call x as, let's see. So we can say from the beginning, we can say convert. I can do a better job than that. Convert back to x. I'm going to convert back to x. So what are we going to, we can say tangent theta was 2x. So tangent theta was 2x. I can just put a 1 in the denominator because when you divide with 1, you're not really changing anything. So my triangle is here. This is where the tangent is. Tangent is opposite over adjacent. And I'm going to have 4x squared plus 1. Okay, 4x squared plus 1. All right, so I'm ready to plug everything back into in terms of x. So we're left with 1/2. So final answer is in blue, and I'm plugging everything back in the highlighted answer in terms of x. Secant theta would be, cosine is adjacent over hypotenuse. Secant theta would be hypotenuse over adjacent, which is just square root of 4x squared plus 1. Plus tangent theta would be opposite over adjacent, which is 2x over 1 plus a c. And that's it. That's our integral. I believe this was the last example for evaluating integrals using trigonometric substitutions. One more time, for some integrals, more than one technique would work. You need to decide which one is faster or easier. Use that technique to evaluate that particular integral.